We often use series and Taylor polynomials to approximate values. And when you do an approximation, remember, there's always an error involved between the actual value of something and the approximation you get. Now in this video I want to talk mostly about errors involving Taylor polynomials, but let's just start by reviewing the error involved in approximating the sum of an alternating series. We've already talked about this in a previous video, but this is going to lead into approximation errors with Taylor polynomials. Remember that we can test an alternating series for convergence through the alternating series test, meaning that the terms have to decrease and the limit of the kth term is 0. And once we know it converges, we can approximate our sum using a partial sum, using the sum of n terms. And we know from our discussion that the error between the actual sum and the partial sum is less than the first term that we don't include in our partial sum. Just as a review of that, I have here an alternating series which I've already checked for convergence. It does converge by the alternating series test. And what I want to do is I want to estimate the sum of this series. If I write some of the terms out, I'm going to estimate the sum by calculating the sum of the first 4 terms. And I've done that in advance. The sum of those 4 terms would be this. And based on what we've talked about before, the error between the actual sum and my estimate we know is less than our first missed term, which in this case is the 5th term. In other words, our error is going to be less than, this value is 1 over 120. And so based on that, we know that our sum would be somewhere between these two values. So that's a quick review on estimating the sum of an infinite alternating series and the error involved in that estimate. Our error is less than the first term we don't include in our estimate. So now I want to talk about approximating values with Taylor polynomials. And again, the idea is the same here in that there will be a difference between the actual value of a function, the series, which goes on endlessly, and our approximation, which is finite. The positive difference between those two we call our remainder or our error. The Taylor series goes on endlessly. The Taylor polynomial has a finite end. The extra is our error. So the question is there a way to determine how big our error is as there was with alternating series? And there is. We can find the amount or bound of the error using what we call the Lagrange error bound. And here's what the Lagrange error bound says. The error between the actual value of f at x and our Taylor polynomial at x, the positive difference is our remainder, our error, and our error is going to be less than this formula, which is the Lagrange error bound, where m is the largest value of this. Now this looks quite complicated, so let me just try to break this down. The way I like to think about this formula is that it's basically the same as the first term that's not included in our estimate on our Taylor polynomial. So you'll notice how with your Taylor polynomial your last term would be this. Your n plus first term would be this formula if you take a look at it. The m is the n plus first derivative, and what this is saying is that it's the largest n plus first derivative of all values between the point your Taylor polynomial was set up at, x equals a, and the value you are approximating. So m is the biggest n plus first derivative for all values between our starting point a and where our estimate is at x. So what I'm saying below here is that a way to remember this formula is similar to the way we can remember our alternating series error bound, that the error is like the first term we didn't include in our estimate, the n plus first term. So if this was the nth term of our Taylor polynomial, the n plus first term would have been this. So the Lagrange error bound formula looks quite complicated. Let's do a couple of examples just to try to break down what it means. So we have a function that has 5 derivatives on an interval between 2 and 2.9, and we're given some information here about the 5th derivative. And we're told that the 4th degree Taylor polynomial for f about x equals 2 is used to approximate f at x equals 2.9. So what we're saying is that the actual value of f of 2.9 is being approximated by the Taylor polynomial, the 4th degree Taylor polynomial at 2.9, and there will be a difference between these two. That absolute distance is our error r, using the 4th degree Taylor polynomial. Now we have a formula for the error, the Lagrange error bound, so let's just write that up again. Our error will be less than or equal to the biggest value of the n plus first derivative, which I call m. So I'm just going to put the n plus first derivative in here for all values on the interval, which I'm using z to represent all values between 2 and 2.9 in this case, divided by n plus 1 factorial times the absolute value of x minus a to the n plus 1. This is our m, our maximum n plus first derivative on the interval. So n is the Taylor polynomial that we're using for our approximation, which is a 4th degree Taylor polynomial. Our error, using a 4th degree Taylor polynomial of x equals 2.9, will be less than or equal to, our n is 4, so we're going to use the 5th derivative, the biggest 5th derivative on the interval from 2 to 2.9, which we'll come to in a minute, over n, 4 plus 1, 5 factorial, times x is our value we're estimating, 2.9, minus a is the center of the Taylor polynomial, 2, to the 4 plus 1, 5. All right, the only thing we're still wondering about is this value. This is the biggest 5th derivative. Well, we were told that up here. We're saying that on the interval, for all x, which I'm using z here, for all values of x on this interval, the biggest derivative is 0.8. So I'm going to put 0.8 into position. And if I then calculate this out, I can see that the difference between the actual value of f of 2.9 and my approximated value, p of 2.9, will be less than this value right here. Let's do an example now where we do an actual approximation of a value. We want to approximate the value of sine of 4 degrees accurate to 5 decimal places. And we're going to do this using a Taylor polynomial. And we know that the Maclaurin series for sine is this. Goes on endlessly. Now if we wanted to know the value of sine of 4 degrees, we could plug not 4, but the radian equivalent of 4 degrees, 4 pi over 180, in for our x's, and if we did this endlessly, we'd get the exact value. Now that's obviously impossible to do it endlessly, so what we're going to do is approximate it using a Taylor polynomial, which is a fixed number of terms, but we need to know how many terms do we need of this in order to get an answer accurate to 5 decimals. By the way, remember that our angle needs to be in radians because our derivatives, which are part of the Maclaurin series, were determined based on that. So what we're saying is that the difference between the actual value of sine of 4 degrees and our Taylor polynomial approximation using an nth degree polynomial. We don't yet know which degree of polynomial we need. We don't know how many terms. Our approximation using that, we want that to be less than or equal to 5 decimals of accuracy, which means that this value needs to be like that to account for rounding off. In other words, we're saying that the error using the nth degree polynomial of this value needs to be this. And of course we have the formula for our error, which is the maximum n plus first derivative of all values of x on the interval divided by n plus 1 factorial times x minus a to the n plus 1. We want that to be less than or equal to this value. Now, since we're using a Maclaurin polynomial centered at x equals 0, we know that a is 0. We know that x is the value we're approximating. We're just narrowing down what all these are. We don't know what degree of polynomial we're using, so we don't know n. In terms of the n plus first derivative, we'd be talking about the derivative of sine. And we know that our original function is sine. Our derivative would be cos. Our second derivative would be negative sine. Now, even though we're looking for the n plus first derivative, we don't know which derivative that is yet. We can see that no matter what the derivative is, it'll be plus or minus sine or cos. And we know that the maximum value of that for any value will be 1. So that will be our value of m, which we can plug into here. So we're slowly narrowing down what everything is. Let's plug this in. We're going to get 1 over n plus 1 factorial times 4 pi over 180 minus 0, which is that to the n plus 1, and we want that to be less than this value. Now, we can estimate the value of n through a calculator, putting in different values of n to make sure that this side is smaller than this side. So I'm just going to put this formula into my y1, and then on my table, look for the value of n that makes this less than this. And if I go down here, 2 is not quite big enough, but 3, 9 times 10 to the negative 7, will make this smaller than this. So what this is saying is use a third degree Taylor polynomial to approximate sine x, and your approximation will be accurate to 5 decimal places. Let's see. So our third degree Taylor polynomial for sine, which we know is this, or would be this. Let's now plug in 4 degrees in radian mode. So plugging that in for x. There's my angle. I've just stored it so I can use it multiple times. And now I want to find the value of a minus a cubed divided by 3 factorial, which is 6. The actual value of sine 4 degrees, or at least as close as the calculator can get, since this is an irrational value, is that. And the difference between these two should be accurate to 5 decimal places. The actual minus the estimate, definitely within 5 decimal places of accuracy.